In the book The Design of Experiments, published in 1935, Ronald Fisher presented the following situation. In a tea party, a lady claimed that when she tastes tea, she can tell the difference between when the tea is prepared serving milk first and then tea, or tea first and then milk. Fisher was suspicious and he decided to develop a test of significance to determine whether this is true or false. Regarding the test of significance, Fisher made this very important statement. In considering the appropriateness of any experimental design, it is always needful to forecast all possible results and to have decided without ambiguity what interpretation should be placed upon each of them. So this is very important. So we need to develop a test of significance, and the test needs to forecast all possible results. And then before we run the test, we need to place to each possible result one interpretation. And the interpretation has only two possibilities. If this result occurs, then this shows that there is a significant effect. And if these other results occur, then the test shows that there is no significant effect. So let's see what test of significance Ronald Fisher developed to test the claim of this lady. The test consisted on presenting 8 cups of tea, in which 4 of them were prepared by serving milk first and then tea, and the other 4 the other way around, tea first and then milk. And the task of this lady would be to separate the 8 cups of tea into 2 groups. 4 would be the group of milk first, and 4 for tea first. Now, what Fisher also claim that is really important is to put that nothing else except these 2 possibilities, milk first and tea first, influences the experiment. So for example, if you put a lot more sugar in the tea first than in the milk first, then there is a confounding variable. It's not only tea first, but there is also more sugar. So if a person classifies the cups of tea as milk first, it may be the case that she's doing that because she tasted the differences on sugar, not in the way it was prepared. So he says, keep everything constant, except that in 4 of them there is milk prepared with milk first and tea first, and the other tea second, and the other one tea first, milk second. But in order to make sure, not only keep everything similar, but there may be some other variables that we don't know that they may be affecting. So the order of presentation of the cups of tea should be decided by a random allocation. Okay, so this is the test. Now, Fisher also said we need to determine all the possible results of the test, and for each of the possible results to determine whether it shows that there is a significant effect or not. Okay, so in order to do that, what we need to think is, what would happen if someone with no knowledge whatsoever of how you serve the tea does the classification. So someone with no capacities of discrimination. Let's put a baby doing the classification without even testing, for example. And he says, well, we need to consider what is called a null hypothesis. The null hypothesis in this case would be that the lady cannot tell the difference between milk first and tea first. There is an alternative hypothesis, that the lady can tell the difference. But this hypothesis, says Fisher, cannot be tested because it is inexact. Why is it inexact? Well, because when we say that the lady doesn't have the capacity of differentiating between tea first and milk first, that's one exact value. There is no capacity whatsoever. But when we say that the lady can have some discriminatory capacity, well, is it that she would do that 100% of the time, 80% of the time, 70% of the time? We don't have the possibility to establish that with exactness. So because we cannot exactly establish an alternative hypothesis, the only thing we can do is to propose a null hypothesis and to test whether the null hypothesis is true or false. And this is the beginning of the very, very important approach in statistics. That's the approach that in psychology has been used since the 1940s. The null hypothesis significance testing approach, or NHST. Okay, let's see how it works in this example. Okay, so let's say we ask someone without no knowledge to do this classification. This is one possible classification. Caps A, B, and C, D go one side, and E, F, G, H to the other side. Now, this is one possibility. But what happens if someone without knowledge does this millions of times? Well, what are all the possible classifications? How many correct choices in each classification? So let's start answering those questions. Okay, so we can start and note all the possibilities of classification. So in the group of milk first, we put the caps A, B, C, and D, and then tea first, E, F, G, H. A second possible classification is A, B, C, D for milk first, E, F, H, G in tea first. A third possible classification is A, B, C, D in milk first, and E, G, F, H. So we are changing the order here. We can start doing that and write down all the possible classifications. But this would be very, very long. This is not a good strategy because this would lead to 40,320 possibilities. Instead of writing down each possibility, we need to come up with a mathematical calculation of all the possible values. And this is quite easy actually. So let's say you have to decide which cap to put first in the first place. So there are actually 8 possibilities. You can put A, you can put B, you can put C, D, E, F, G, H. So let's say you put A as the one in place number 1. So now you only have 7 possibilities. So if you place A in position 1, then you can place B, C, D, E, F, G, or H in position 2, but you cannot put A again. So you have 7 possibilities. And see that if you put A in position 1, then you've got 7 possibilities for or to position a cap in position 2. But then you have to do the same for all the 8 possibilities in position 1. So you have to repeat everything I'm going to say for B, for C, for D, E, F, G, and H. So now you put A in position 1, B in position 2, so now you have 6 possibilities for position 3. And then you've got 5 possibilities for position 4, and then so on and so forth. So by doing this calculation, A times 7 times 6 times 5 times 4 times 3 times 2 times 1, that gives us all the possible combinations, 40,320. So it was a good idea to stop writing down all the possibilities and come up with a numerical solution. Now, this is actually incorrect. These are not all the possibilities, because think about it. Let's say you put A in position 1, B in position 2, C in position 3, D in position 4, and we said that for the rest, the position doesn't matter. So we don't have to do times 4 times 3 times 2 times 1. So we've got 8 times 7 times 6 times 5. So we've got 1,680 possibilities. But again, this is not correct, because we said that the order that we put the caps in each of the groups doesn't matter. So it doesn't matter if it is A, B, C, D or A, C, B, D, this would be considered the same. And actually there are 24 possibilities. So we have to divide the value we obtain, 1,680, or 8 times 7 times 6 times 5, by 24. Or more elegant, 4 times 3 times 2 times 1, which is 24. So that gives us the total number of possible combinations, which is 70. So now we've got what Fisher indicated. We need to indicate before running the experiment all the possible outcomes of that experiment. So we know that we've got 70 possible outcomes. Now we need to dig into that a bit further. We need to know how many correct choices would be in each of these 70 outcomes. And this table gives us that idea. So let's see this possibility. In the first group of milk first, we put A, B, E, and H, which are the 4 with milk first. And in the second group, T first, we put the C, D, F, G, which are the 4 with T first. So how many correct choices are there? All of them. So the 8 were correctly placed in the group. Now, how many combinations are of this type? Well, only one, because remember that order doesn't matter. So it doesn't matter if we put A, B, E, H, or A, E, B, H, or A, H. So these are not possible. We are not considered anymore within this 70 total. So there is only one combination in which there is 8 correct choices. Now let's see combinations in which we've got 6 correct choices. So it would be to have 3 milk first and 1 T first, classified in the milk first group, and 3 T first and 1 milk first, classified as in the T first group. So of these options, we've got 16 possibilities. And what about options in which we've got 2 correct in each group? Well, these are of this type. 2 of milk first and 2 of T first in the milk first group, and 2 of T first and 2 of milk first in the T first group. And these are 36 combinations are of this type. Now, why did I say that there is only one combination in the first in the first row and more than one combinations in the other two? Well, because we said that the order of the caps doesn't matter, so whether it's A here first or B first, as long as A, B are there, it would be the same combination. But which caps are in each group does matter. So we can have, instead of C, we can have D or F or G here. So these are 4 possibilities. And then instead of having ABE, we can have ABH. So it's a different cap. Or we can have AEH. Or we can have BEH. So the present one plus the other 3 that I just mentioned. So these are 4 possibilities. And if you consider 4 possibilities of the MIG first and then 4 possible options for T first, then that's 4 times 4, which is 16. And a similar consideration goes to this case. So here we can have A and B, A and E, A and H, B and E, B and H, and E and H. And here, same thing. We can have C and F, C and G, and C and D, which is the present one. We can have DF, DG, and FG. So we've got 6 ways in which we can have 2 MIG first, and 6 ways in which we can have T first in this group. So that's 6 times 6, which is 36. And the same occurs with combinations in which I have only 1 MIG first in the MIG first group, or no MIG first in the first group. So basically, these are the possibilities. Remember, if someone is who doesn't have any discriminatory capacities, or even is not tasting the tea, is doing the classifications, well, of the 70 possible cases, in one possibility, it is going to be the 8 correct. So what's the probability of obtaining 8 correct choices out of 70 possibilities? Well, it's 1 in 70. So obtaining 8 correct is an event that happens 1 in 70 times in someone who doesn't have knowledge. And 1 in 70, or 1 divided by 70, is 0.014, or we can say 1.4% chance. What about 3 correct classifications, like in this case? Well, that happens in 16 out of 70. But typically what we are interested in, whether if we do 3 correct combinations or more, so that would, or which would be 4 correct combinations. So that's 16 plus 1, 17. So obtaining 6 correct or more happens 17 in 70 times. And that is 0.243 or 24.3%. So now Fisher says something very, very important. Before running the experiment, the researcher decides which result would be significant. And basically here, it is the choice of the researcher. There is no magic number. It's arbitrary. The researcher decides which of these outcomes would be a significant result. If we decide that we are going to reject the null hypothesis. Remember, the null hypothesis is that the lady doesn't have any discriminatory skills, so she cannot tell the difference between milk first and tea first. So we are only going to reject that hypothesis if she gets the 8 correct, the 8 classifications correct. Then what is the probability that someone without knowledge would have 8 correct? Well, we said that 1 in 70, and that's 0.014 chance. Well, the researcher may decide that we are comfortable with that, so we decide that that is a significant result. Significant result means that we are going to reject the null hypothesis. What about 6 correct classifications or more, so 6 or 8? Well, there are 16 plus 1 possible combinations in which someone can get that by chance, so that's 17 in 70, and that is quite high. So someone that doesn't have any knowledge can classify 6 correct caps without having any knowledge, and that happens 17 out of 70 times. A researcher wouldn't be comfortable with rejecting the null hypothesis with that higher chance to getting that result by chance, so it's not a significant result. And of course, if it is less than that, 4 correct classifications, 2 correct classifications, and 0 correct classifications, then of course this would not be significant either. So only we would determine that we obtain the result is significant, we reject the null hypothesis that the lady doesn't have discriminatory skills if she gets the 8 cups of tea correctly classified. Now, this seems like not a very good test. You should add at least 2 more caps in order to be able to have a bit of leeway, because she has to get 100% correct, and it's a bit unfair. You can have a good discriminatory skill, you can get a wrong classification, but you by mistake, but you still have good discriminatory skills. But in this case, one mistake, it already determines that it's not significant. So at least add 2 more caps, and you can make 1 mistake, and the result would still be significant.